All right, so officially welcome everybody. This is, I believe, 99 Flow Talk, where Flow stands for Federated Learning one-word seminar, and we created this seminar together with Peter Richter, Gwen Julia Smith, Orlane Bellet, and Dan Alistar, and Sebastian Stich to provide a global online forum for dissemination of latest scientific research in all aspects of federated learning. This including, but not limited to, distributed optimization, algorithms, privacy, cryptography, personalization, communication, and model compression, system hardware, and other different perspectives. So today it's my great pleasure to introduce you our speaker, Berivan Isik. Berivan is a four-year PhD student in electrical engineering department at Stanford University, advised by Sahi Weissman. So she's supported by many prestigious fellowships, such as Stanford graduate or fellowship or Google PhD fellowship, also won meta research grant. And in her research interest, she is interested in scalable and trustworthy machine learning, information theory, privacy, and compression. And more recently, she's been working on federated learning, model compression, learned data compression, differential privacy, robustness, and fairness in machine learning. So all the relevant topic that we are discussing in this seminar. And today, Berivan will tell us more about her recent work that got published at iClear this year, titled Sparse Random Networks for Communication Efficient Federated Learning. So thank you everyone to agreeing to give a talk at the seminar. I'm looking forward to it.
Thank you so much for the introduction. So I will talk about our recent iClear paper, Sparse Random Networks for Communication Efficient Federated Learning. So in this work, we propose a way of finding sparse networks or subnetworks with random weights in the federated learning setting in a communication efficient way with some other benefits as well. And before diving into details of this work, I want to give you like a very quick overview of some of the works on like sparsification works in the centralized setting and how some of these ideas have been applied in the federated setting, the challenges the federated learning brings when we want to deal with sparsity and the solutions. So maybe the most popular method in model compression in the centralized setting is model pruning. I am sure all of you have heard of this before, but the general framework is we train, so this is centralized setting again, it's not federated yet. We initialize a model and then we train it until full convergence and we achieve, let's say, good accuracy, let's say 90% accuracy. And then we prune some of the parameters. We get rid of or we set some of the parameters to 0. And we can do this like using different salience methods. And one popular approach is to just look at the magnitudes of the parameters and just set the smallest ones, maybe 90% smallest ones to 0 and keep the remaining ones as is. And with this approach, we can sometimes like preserve the full accuracy, like the initial accuracy that we had. Sometimes we need to do some retraining of these remaining parameters, but it's a very successful and powerful method because we are getting rid of sometimes 90, 95, 99% of the parameters and still achieve a good accuracy. So again, this method is really successful, especially on vision domain in the centralized setting. And there have been some interest in applying this method in federated learning as well. So of course, there is this approach of sparsifying the model updates in federated learning at every communication round. So the client does some local training, and when it wants to communicate the model updates to the server, it can sparsify the updates using the same salience metrics, let's say like magnitude or maybe some more like sensitivity terms. But that's not what I'm talking about here. So there are also other applications of model pruning in federated learning where the goal is to actually train a sparse network. So it's not just sparsifying the updates, but the end goal is to actually work with a sparse model at the server side, at the client side, and also during communication. So one example to this is this Prune FL paper, and they propose a two-stage approach. The first stage is like they pick a client, a trusted client, and they let this client to train a model locally on their local data set. And then that client first, trains the model to full convergence, and then it prunes the model. So it's the same approach that we discussed in the previous slide. We have a fully trained model, but it's trained on the local data set, and then we prune them by looking at the magnitude. And then this trusted client sends this pruned model or the mask that they found, they extracted, to the server. And then the server used this pruned model to start the second stage. And the second stage, each client receives this pruned model, and they keep training this. They need to train it because the initial pruned model is actually trained only on one client's data set. So we need further training. So they train it further by also like pruning gradually more and more. So it's a two-stage approach, and it has, I think, like maybe pros and cons. So one benefit is obvious, like in the second stage where the actual learning happens, we have communication gain because the clients and the servers, they all agree that the initial model is already pruned, so they don't have to communicate any unnecessary updates. They only work with a sparse model. But then one disadvantage or one thing to maybe keep in mind is that we assume that we have a trusted client here. And we also assume that this client can train a model to full convergence with their limited local data. So this space is, I think, still open, and there are many things to consider. I see this approach as like a work in progress. I'm sure we will see a lot of improvements. So another approach in the centralized setting. So we are back to the centralized setting again. There's another phenomenon called lottery ticket hypothesis. So it's related to pruning. The authors of this like initial lottery ticket hypothesis papers asked the following question. So we know that we can randomly initialize a model, train it to full accuracy, a full convergence, and then if we can like do the pruning correctly, like say we pick a good threshold to prune the parameters by magnitude, then we can preserve the accuracy. So we know that we have been knowing this like for a long time. But then they ask the following question. So this final model has a very sparse architecture. It maybe only has 10 or 5% of the parameters. The others are all set to 0, and it performs well. So then they ask the following question, like, what if we start the training with this architecture to begin with? So they tried two things. The first thing they tried is they train the model, then they prune it, and they have this architecture. They have this sparse model, which has a good accuracy. They say, okay, let's pick this architecture, the same architecture. Let's initialize the weights and try to train this to full convergence and see if we can still achieve a good accuracy. Maybe like the question here, or the thing that they are trying to test is maybe this architecture is like the good architecture that we should work with. But then they couldn't get a very good accuracy. There was a significant accuracy drop when they picked the pruned architecture, but with randomly initialized weights. But then they tried a second experiment. So in the second experiment, they trained the same architecture, but they didn't randomly initialize it. They just they used the same initialization that they used in the first model. So what they do is they randomly initialize a model, they train it, then they prune it to extract, let's say, a mask or an architecture. And they show that with this architecture, if we were to start with this architecture to begin with, and if we were to use the same initialization that we used in the beginning, then we can recover the accuracy. So what this says is there are some subnetworks. So when we randomly initialize a model, there are some subnetworks that will give us really good accuracy as if we train the dense model and prune it afterwards. But we need to match this sparse architecture and the random initial values correctly. Like if the initialization and the architecture that we are using do not match, currently we don't have a way of getting a good accuracy. So that actually like led to many interesting works afterwards. And the third method that I will talk about, so we talked about pruning and lottery ticket hypothesis. I will mention a third one, which will be the base of our work. It's also like it was developed on top of this lottery ticket hypothesis idea. Okay, so the lottery ticket work is like, it's just suggesting that there are subnetworks in the randomly initialized model. It's not easy to find these subnetworks because the subnetwork that we should use depends on the initialization, depends on the initial values of the parameters. And currently we don't have a very computationally efficient way of finding those subnetworks, except that training this dense network until full convergence and then pruning it. So it is an interesting idea, but we don't have an easy and efficient way of finding these subnetworks. And there have been some applications in federated learning as well. So this is just one example, but as far as I know, there are a few more papers on this space. So this is the federated learning application. And what they propose in this paper is, so here each client has their own lottery ticket network. So meaning that the server maybe trains a dense model, but each client is responsible for a different subnetwork of this global model. And at every round, each client only updates the subnetwork that they're responsible for. And in the second round, they receive like the updated parameters only for this subnetwork from the server. And at every round, the client actually performs like the same operation that I showed you in this previous slide. So they set the parameters to their initial values, they train it to full convergence, and they prune it a little bit more, and then they communicate this update to the server. So it's a way of, I think, running this like lottery ticket hypothesis idea on the federated learning setting. It's communication efficient because each client works with a subnetwork, a sparse network, but it also has this like, I think, implicit assumption that the client can do some local training with their limited local data set at every round. It has some limitations, but it's still, I think, a promising direction. If there are any questions up to this point, I'm happy to answer, because after this, I will talk more about our work. Okay, maybe not.
Yeah, there are for now no questions in the chat or raise hands.
Okay, great. Okay, so finally, there is this like third, let's say, phenomenon in like sparsifying neural networks in the centralized setting. And that's what we try to adapt in federated learning in our paper. So this is, again, like related to the lottery ticket hypothesis idea. But it has some like tangentially different, I think, motivation. So I'm just citing two papers here, but I think there are a few more in this space. What they study or what they try to understand is, okay, we know that when we randomly initialize a model, we know that there are some subnetworks that can be trained to a really good accuracy. Like if we can match the subnetwork architecture and the initialization. But what they try to understand in these two papers is they ask the question, if there are some subnetworks inside the randomly initialized model that can work well without training. So they ask the following question. So let's say we randomly initialize a dense model like this. So this is a dense model. You know, that there is, yeah, we just randomly initialize all the parameters of this dense model. And the idea is to just extract some of these parameters and get rid of the rest. So we will end up with a subnetwork, but still with the random weights. And this subnetwork performs well on our test. So there won't be any training of the parameters, but we need a way of finding these subnetworks. So they test this idea. So they propose slightly different approaches to find these subnetworks. One of them, for example, like assign some scores to each connection in the beginning, and then this scores determines whether this connection should stay in the subnetwork or not. That's what they train. So they actually do some training, but not to train the parameters or like the values of these parameters, but they train, let's say, the probability of each connection staying in the subnetwork or not. So like just to wrap up, what they study is the following phenomena. So we randomly initialize a dense network, and then we freeze the parameters. We never train them, we never tune the parameters. The parameters always stay the same. But then we try to find which connections we should pick to achieve a good performance. And if you look at these plots, so the orange curve, the flat curve, and the other blue flat curve here, they correspond to like training the dense model using different optimization methods. One is SGD, one is ADAM. So this is, let's say these are our baselines. And then the red, the other red and the blue curve corresponds to trying this subnetwork idea. So they try to extract a subnetwork with different, let's say, fraction of parameters. And the difference between the blue and red curve is the way how they initialize these parameters in the beginning. And as you can see, like, for example, in this architecture, with 50% of the weights, they can actually achieve almost the same accuracy. So this means that, you know, they use the same random initial model. The orange curve and the blue curve here trains the parameters of this dense model, but these two actually does not train the parameter, but they just try to get rid of 50% of the parameters in a smart way. And they end up with like 50% sparse random network that performs as well as the baseline methods. And we can see the same thing in the other architecture. Actually, it even outperforms the baselines at some sparse levels. Well, that was also like an interesting observation. It's maybe like a little bit more ambitious than the lottery ticket hypothesis idea, because this one doesn't require training the parameters, but it's still computationally not more efficient than training a dense network, because we actually have to do some training to find these connections. So there is also like a theoretical study of this. So, and in this paper, in this NERPS paper, they ask the following question. So let's say we have like a target subnetwork architecture, a target number of parameters that we want to end up with once we find the subnetwork. Then how large the initial dense model should be, so that we can find these subnetworks with random weights that works well. And they have some, I think, good analysis of this problem, and they work with you know, 2-layer linear and 2-layer ReLU networks, and they prove that like there is indeed like some relation between like the scale of your original dense model and the subnetwork architecture you can get by just like working with the random weights. So this is like still, I think, an area that is open to exploration. And in our work, we try to use this idea to first test if we can find these subnetworks with random weights in a federated learning setting, because it will be more challenging. Each client will have a non-IID data set. Maybe this like training framework will break when the clients like have different updates from their different data set distributions. First, like we show that we can indeed find these subnetworks with random weights in the federated learning setting. And then we also show that we can do it in a communication efficient way. So this is like what we tried to show in our iClear paper. It was a joint work with Francesco from University of Padova, Dennis from Imperial College London, Saki from Stanford, and Michele from University of Padova. So again, our contribution is like, we first show that this idea also works in the federated learning setting in the challenging settings, like with non-IID data, with partial participation from clients, we can still find these subnetworks with random weights without touching the parameters, values of the parameters. And we can do it in a communication efficient way. So we show that we can find these subnetworks by spending less than 1 bit per parameter. And we can also compare it with other compression methods like QSGD, SignSGD, or more recent ones like Drive that performs around the same bitrate, 1 bit per parameter. But of course, they train dense models, so they don't try to find any subnetwork or anything. They just train a dense model and they communicate model updates. They just compress these model updates around the same bitrate that we are using, and we show that we can outperform them, which is, I think, a little bit surprising because they actually train the parameters, whereas we are just trying to find a subnetwork with a correct initialization. We also empirically show that our convergence is faster than our baselines. And also we have this bonus of like efficient representation of the final model, because at the end, we just learn a sparse model. And with the correct initialization, we can actually show that we can use less than 1 bit per parameter to represent the final model. And also it comes with some efficient computation, efficient inference. I will talk about these later in the slides. Okay, so the general framework is like more or less given in this slide. So at the server side, so the server initializes this dense model with random weights. And as I said, once we initialize the model, the parameters will never be trained. So we will freeze these parameters. They will be fixed throughout the training. And each client has a copy of this same randomly weighted dense network. And we can do this with like some shared random seed. So we can just assume that the server and all the clients have a copy of the same randomly weighted dense network, and everyone freezes these parameters. So we will never be touching the values of the parameters in this network. And instead, the clients will collaborate on learning a probability mask. So this probability mask has the same architecture as the dense model that we initialize. And so the probability mask, has probability assigned to each connection. So this, for example, we have like a value between 0 and 1 here that indicates the probability of this parameter staying in the subnetwork or not. And this is what we train. So the server will keep like a global probability mask, and at every round, this global probability mask will be communicated to the clients. The clients will do some local training. At the end of the round, they will have a local copy of their probability mask that they want to communicate to the server. And I will talk about like how we do it in a communication efficient way. But I first want to talk about like how we actually train this probability mask at the client side. So at each forward pass, what each client does is, so they take this probability mask and they extract a binary mask. So this binary mask is a sample from a Bernoulli distribution parameterized by their probability mask. So this is a binary mask that they can use to sparsify this randomly weighted dense network. So at every forward pass, the client just take a Bernoulli sample and use this mask to sparsify the dense network to end up with a sparse network or a subnetwork of the originally randomly weighted dense network. So then they use this subnetwork with random weights to do their forward pass, to compute the loss, and then backpropagate this loss to update the probabilities, not to update the parameters. So the loss is never propagated to update the parameters of the network. They just propagate the loss to update the probabilities. And they repeat it, let's say, for like some number of epochs, and at the end of each round, they end up with a slightly different probability mask. And the goal of the server is to collect some information from the clients to update the global probability mask somehow. And we want to do it in a communication efficient way. Of course, like if we just communicate like the probabilities of these masks, then we will not gain any communication gain, because we need to spend like whatever the precision we are using for each parameter. So it won't be very different from just communicating model updates without any compression. So instead, what we do is the following. So we assume that the goal of the server is to estimate the average of the probability mask across all clients. And to do that in a communication efficient way, we say that each client, each client has a different local probability mask. And they take a Bernoulli sample. They take a sample from a Bernoulli distribution, sample from their local probability mask, and then they communicate this binary sample to the server. So the server only collects like a binary sample from the probability mask of each client, and then it aggregates these samples. And we can show that this aggregation is like an unbiased estimate of the true mean, and we can show that the error is also upper bounded. So here, one point that I want to highlight is, in the worst case, we have to spend 1 bit per parameter to communicate this binary mask. But we can do a better job here because the mask that we are communicating here, so 0 and 1 values, they indicate, so they are like samples of a Bernoulli distribution, and the parameters of the Bernoulli distributions actually indicate like whether a particular connection should stay in the network or not. So for example, in the sign SGD case, when we communicate like a binary message to server, each binary value indicates whether this update is positive or negative, and we have a symmetry, and we have to like actually spend 1 bit per parameter, more or less. But in our case, each binary value actually indicates whether this connection should stay in the subnetwork or not. So
Berivan, can I ask a question? So let me just, does the camera work? Okay. So so you say that you're turning off the connections, or you're turning off the neurons, and then all the connections from a single neuron? Because my understanding was that what I thought was that this theta has exactly the same dimensionality as the number of the parameters, not the links.
Exactly, exactly. So we have a probability assigned to each connection, not each neuron. So this mask that we are actually trying has the same dimension as the model. That is correct. Was that your question?
Okay.
So let's say we have like the parameters, and then each probability mask has like the continuous values between 0 and 1.
Okay, I just wanted to clarify that. Thank you.
Yeah. So and what we want to communicate is a sample from these distributions. So what I was trying to say is like each binary value here indicates like whether a particular connection should stay in the subnetwork or not. So we don't actually necessarily have a symmetry. So the entropy is actually smaller than 1 here. So by doing like some clever entropy coding, we can actually spend much less than 1 bit per parameter. And we actually like tried arithmetic coding, and we could actually like reduce the bit rate down to 0.8 bit rate. So instead of like spending 1 bit per parameter to communicate a binary value for each connection, we can get some extra gain here. Okay, so as I said, we have like this unbiased estimation, and we can also upper bound the error for like to have some convergence analysis. So I also want to highlight that so the way how we initialize these dense networks is very important here, because at the end, like we initialize this model and then we never train any parameters. So if we have like a really bad initialization, we may never be able to find like a good subnetwork that works well. So in the initial paper that actually introduced this idea of training or finding subnetworks with random weights, they tried different random initializations, and they found out that this method, sampling like, sampling, okay, so they found the following random initialization method very powerful compared to others. So what they do is they take a sample from this K-mean normal distribution. Let's say it's so they just take the standard deviation of the K-mean normal distribution, and then the initial value of each parameter is sampled from this uniform distribution. So it's either sigma or minus sigma. So we actually have this also like quantization in the initial parameters. which makes the final model very efficient in inference time. So that's how we initialize it. And so compared to other initialization methods, it actually helps with like finding good subnetworks. So here, so one thing is like, as I said, like we need to initialize them in a smart way so that we can find subnetworks. And another thing is like, for example, since we have this quantization here, at the end of training, we end up with a subnetwork, for example, like this one, the subnetwork, with bunch of parameters set to 0. We never use them. And the others are either sigma or minus sigma. So we have this ternary representation in the final model, which makes the storage and also like computation on these models very efficient. I think there's a question. I can take the question now.
Yes, let me unmute Mohammed.
Hi, Berivan. Thank you for the interesting presentation so far. I just have a question about how do you backpropagate the error when it comes to training the masks, because I can see that there's some sampling from a Bernoulli distribution, and it's not clear for me how do you propagate the error through the sampling procedure. So could you please elaborate on that? Thanks.
Yeah, sure. That's a good question. So before answering your question, we skipped like a small detail here. So we have the probability mask here that we want to train, but we also have like this hidden mask here that I didn't put in the slide for simplicity. So this hidden mask actually has a continuous score. So it has the same dimension as the probability mask, but it has continuous values, not limited to 0-1 range. And that's actually what we train. And then we extract the probability mask by passing that through a sigmoid function to get values between 0 and 1. So what we actually train, so we actually propagate the loss up to that point, and then we extract the probability mask at the end of each round by just passing it through a sigmoid function. And so you're right that we have to do a little trick when we work with the Bernoulli sampling here. We use a straight-through estimator here during backpropagation. So we just use like so we just, propagate the gradient of this mask by assuming like an identity relation to the parameters. Okay. That was a good question. Yeah, we have the details in the paper, but I skipped some details in the talk.
Maybe can I have a follow-up question, please? So since your actually output is probability, so our probabilities with respect to each weight, how do you evaluate them? Do you just take many random samples and average that, or how do you do the evaluation?
I see. So we have two ways of evaluations, and we report results with both approaches. So one is the server just, the server has this like global probabilities, and it takes a random sample just once, and we do the test on this model. The second one is we actually threshold these probabilities. So we can just set the threshold to 0.5, 0.6, maybe 0.7. It's like a more deterministic approach. We saw that like sometimes like one of these methods works better for some settings. Maybe that's also something we should, improve later. But your idea is also makes sense. I think like sampling multiple times and averaging them would be maybe a more robust way of reporting the performance.
Thank
you. Okay. Yeah. So I think like the summary of the slide is like the way how we initialize these models is actually important, and it affects the performance of the final model. Okay. So let me give you some experimental results before I move on to the next topic, like the way how we actually aggregate these updates. Okay, so we tried these models, this framework on like Cypher10, Cypher100, MNIST, and eMNIST dataset. So here our baselines are like some old methods like QSGD and SignSGD, and some more recent ones like Drive and Eden. they all like work around the same bitrate, around 1 bits per parameter. And the blue curve is our method. So we start with like as you see, like we start with 1 bits per parameter in the beginning. And then the bitrate gets smaller and smaller. I think the intuition behind this is like the binary mask that we are communicating is like more symmetric in the beginning because we didn't learn enough, and we actually start with we initialize these probabilities as like 0.5 in the beginning, and then gradually they learn how to assign more extreme probabilities to each parameter, and when we do that, we actually gain from communication too. And if you look at the accuracy plots, we actually have like a faster convergence than most of the methods, and we achieve like a better accuracy. Here, like we actually have this other baseline called FedMask. Maybe this is not as popular as the others yet. This is a recent work. They also like try to train these masks, but in a deterministic way. And it doesn't perform as good as our approach because they don't, so they just assign some scores to the parameters, but everything is deterministic. And I think that that's not the way to go when it comes to deciding which parameters should stay in the subnetwork. And I think this is just the proof of that. And also, if you look at the communication cost, like they cannot do better than 1 bit per parameter because of this like deterministic approach. So all the other methods, all the other baselines are training a dense model. So they don't try to find a subnetwork or anything. They just train the dense model using a method similar to federated averaging, but they compress the updates from before communication. So these are the results on Cypher 10, and we have similar observations in Cypher 100, and we actually have more significant gains in Cypher 100. And then like similar gains in MNIST. It's just Drive and Eden, these two recent methods are sometimes challenging our method when it comes to bitrate. They have sometimes slightly smaller bitrate than our method. And these are the EMNIST results. Again, like we reached like a higher accuracy. But all these results that I showed you so far are on IID dataset with full client participation. So it's a relatively easy setup. And when we switch to non-IID data distribution, and when we also allow some clients to not participate in every round, we actually see like a drop in our performance, and we are not performing as good as our baselines. And we so our guess is that it's because of the way how we aggregate the updates and how we actually update the global model. So initially, what I told you is like we collect these binary samples, we average them to get an estimate of the new global probability mask. And then what we were doing was to actually hard replace the previous global mask with the new one. So we were actually like removing everything we learned. We were getting rid of the history completely. And when we actually deal with this like non-IID data split with like partial client participation, we don't get like a sufficiently informative update at every round. And when we hard replace the previous mask with the new one, we are actually like losing a lot from convergence. So as a solution to that, we propose like a new way of like aggregating these updates. So since like we are actually training a Bernoulli distribution in a sense, we said that, okay, maybe we can like actually use the conjugate distribution, beta distribution, to model this Bernoulli distribution that we are trying to learn. So let's say like this alpha and beta are the parameters of the beta distribution. And then instead of like hard replacing these parameters at every round, we actually like preserve the history information and use our aggregation to update these parameters a little bit. So it's similar to like using gradients to update our models instead of like hard replacing everything at every iteration. And this actually helps a lot with this like more realistic setting when data is non-IID split and when only a fraction of the clients participate at every round. We actually find it useful to reset these parameters at every few rounds. So we start with a uniform distribution, and at every few rounds, we reset them to their initial value. So we've actually let the model to forget some history information at every few rounds. And we have a way of like tuning these parameters. We say it depends on like what fraction of the clients participate at every round and how many rounds you should wait until you collect enough information about your the collection of your data sets. So we have like analysis of like how we should actually update these parameters, at what frequency we should update these parameters in the paper. But I just want to show you like how this actually improves our results. So this is a more realistic setting than the results I showed you before. Here, like we have different levels of like participation ratio. For example, this is like an easy setting where all the clients participate at every round. This is the most challenging setting here, where only 10% of the clients participate. And these different rows indicate the level of non-IIDness. So for example, these results are on Cypher 10. So we have 10 classes. And this row is like when each client has data samples only from 2 classes. So this part is like the most challenging, I think, setting in this table. And this one is the easiest one. And you can see we have like up to 10%, more than 10% gains in accuracy. So here we are looking at only subset of our baselines because these were the most successful ones in the IID experiments. And you can see that we actually have really significant gains in accuracy. I think it was interesting to observe that empirically this method works so well, but there are still theoretical questions like, we don't have a really good way of explaining why these are outperforming this like other compression methods that are working on the dense models. We don't have a very clear explanation on them. But maybe like combining this strategy with some dense training would actually improve results even more. So I can also show you the bitrate in this like more challenging and realistic setting. So we have like up to 10% gain in accuracy, but in terms of bitrate, actually these 2 baselines, Drive and Eden, are again challenging us in the bitrate. So they sometimes like have slightly smaller bitrates, but at the cost of like 5 to 10% accuracy loss. Yeah, so to sum up, we show that like this finding subnetworks with random weights idea works also in the federated learning setting, and it also comes with advantages in the communication gain and efficient computation, efficient representation of the final model. And again, like we have this like fast convergence that we observe empirically, but we don't have any theoretical explanation of why. And there are a number of feature directions, I think, here. So one is, so it's also related to Peter's question. So we are assigning a probability to each connection here, but we can also think of ways to assigning a probability to each neuron, or maybe like to each channel to also impose some structured sparsity. That could also help with the computational efficiency more, because then at every forward pass at the client side, we will actually, so here, this model will have a structured sparsity that can be run faster. So it has like computational advantages. So it's open if that idea will work, if we can still like get good accuracy, if we assign a probability to each neuron or each channel or each attention head, if it's a language model. Another open question is, I think, like once we have this sparse network that performs well, let's say, maybe we can like train these random parameters a little bit to improve the accuracy more. And we can do it in a communication efficient way because the network is already sparse. And the clients and the server agree on the architecture of this sparse network. So we don't actually have to worry too much about communication efficiency there. So that could be something like to improve the accuracy more without compromising a lot from communication. we can also try to do the other way around. Like maybe we have a dense model that is already performing reasonably, and we can try to sparsify it using our method. That is also open because it's not clear if this will, give better results than just pruning the model. So that's also an open question. And the last point is we briefly touch on this part, but it's actually, I think, open to exploration. So when we have this like Bernoulli sampling, both in like each forward pass and also at the communication part, we can actually use this Bernoulli sampling to amplify the privacy when there is a differential privacy mechanism somewhere in our framework. I think that is open. So we have some like initial exploration in this space, like how sampling from a Bernoulli distribution with private parameters can amplify the privacy further, but we didn't exploit this part too much. And I think that's also a promising direction potentially. So I think that's all I want to say. So you can check our paper on arXiv or at open review of and iClear's page. You can also check or play with our code, and you can always let me know, or the other authors, if you have any questions with the code or with the setup, anything. I'm happy to take questions.
Thank you very much for a great talk. We already have one raised hand by Mohammed. Let me try to unmute Mohammed.
Yeah, thank you. I just want to ask about the generalization performance of such approaches when it comes to just training a mask instead of training the weights in the network. Mm-hmm. Just finding those subnetworks compared. So the generalization performance of such an approach compared to, for example, federated averaging without any masking. Do you have any insights on that?
So we don't have any experiments on that.
Okay.
Yeah. So, but we are actually, yeah, I think it's open whether like you can actually jointly train different models with the same sparse mask. So that could work. Yeah.
Sorry. Just my question is based on what in the paper lottery ticket hypothesis that they did. Like basically they trained those subnetworks after finding them, and they just noticed that they have some similar accuracy to training the whole network. So just my question is, if you had, or if you played with the code and tried to just instead to add up in the figures here the performance of Fed average. Without any...
I see. Yeah, so federated averaging is like, it has slightly larger, I think it has like 0.8 accuracy, for example, in this plot. Okay. Yeah, we didn't add it in the plots, but yeah, okay. We are not as good as the federated averaging approach.
Yeah, we're not expected to be that good.
But we have like an extra, compression here in the communication.
Yeah.
That is not present in lottery ticket hypothesis, right?
True. Okay, thank you very much for this interesting.
Thank you. I mean, I think it's worth trying, like what happens if we didn't do any compression at the communication part. Like if we just communicate the probabilities as they are, maybe then it would like coincide with federated averaging.
Yes, maybe I would have one question about the evaluation. So what is actually the underlying optimizer that you're using? Is it just like a SGD, or do you run for all the methods some as well, like some local steps?
Do you mean like during local training?
Yes. So do you actually run local training? Because like in your plots, like you had like a QSGD and all the stuff, and I was not sure whether that by QSGD you mean like when you're communicating you're doing quantization, or whether you're actually running local steps like the same way as Fed averaging or a scaffold or Proxkip would do.
Yeah. So we have like 3 to 5 local epochs at every round, and we use the same number of local epochs for all the methods that we compare to.
Okay. So actually, even for your approach, you do run a local epoch. So it's compatible with running like multiple local steps.
Yeah, exactly.
All right. Thank you. Yeah, clear. And one maybe other question about. just a general evaluation. So once you once you are on central server, once you have this model and probabilities, does it make sense to kind of like although it's going to lead to dense model, does it make sense for evaluation to make some to get like the best model, to make something similar that that random dropout does? That, I mean, like, because this kind of looks like in a sense like a random dropout, that you actually multiplied weights by one of a probability that you would sample them and take that as your full model. Does it make sense here or no?
Yeah, I think that's a good idea. Yeah, we didn't try that, but I think, yeah, that's one way of improving this work, I think. Yeah.
Okay, thank you.
I think, thank you for the idea.
So I have a question. So correct me if I'm wrong. So it's somehow this is based on the observation that these models, these networks before training, they are so over parameterized that we don't need all the weights, right? So
Yeah.
if you do, so let's say you do this, then you find the subnetwork, and then if you do it again on the subnetwork, what would how far you could go, right? Then you do it on that subnetwork, and then you identify yet another subnetwork, and you try to do it on it. I would like to see how quickly this thing really drops down and stops working.
I see. So you say like we will find a subnetwork and then we will run the same algorithm to find a smaller subnetwork.
You have a new network and so on. Because somehow, of course, it cannot go into infinity, right? That's obvious. Yeah. And if, let's say, if people were training, I would say, efficient networks in the sense that they're not so massively over-parameterized that, let's say, most of the weights are not needed at all, then this kind of mechanism would not work, right? So what you're pointing at is that wait, we can just throw many things out. And not only that, we can also initialize randomly. For some reason, we can do well.
Yeah, that's a good idea. It's just so here we are actually learning, like we also learn the sparsity ratio. So we don't specify sparsity ratio in the beginning. We just let the model learn like what probability it will assign to each connection. So for example, at the end of training, let's say like maybe, I don't know, some fraction, maybe 50% of the parameters will have a really, really small probability of staying in the network. So maybe once we get rid of them, I don't know, maybe we can train the remaining ones a little bit more and then sparsify it again. Is that what you're suggesting? Because this is already what the network is suggesting for us to remove. So that's an interesting idea. I just don't know how to enforce even more sparsity here.
Well, what I would, because you output this in the end, because I guess you run these Bernoullis, right? And then some of these things will be zero, and those you drop, and the ones stay, right? But exactly. But I'm just wondering how stable that kind of convergence is, whether then if you just say, okay, now forget about all of these are already zero. You hard constrain them to be zero. You're not going to modify them, whether this will go further or not.
Yeah, that's an interesting idea. Yeah, that's super interesting. Yeah, I don't think there's any work in that space. Yeah, it's worth trying, I think.
Yeah. So this is very interesting that one can initialize in a random way. Of course, you need to have this special distribution. I have no idea how this distribution works. I don't know whether you have any insights on this. Do you have any insights into why this distribution?
No, I think it's mostly based on empirical, just empirical results that it works well. There are so many, I think, questions like to understand why any of these blocks work so well.
If I may just add a point, Berivan?
Yeah, sure.
So hello, I'm Francisco, one of the co-author of the paper. And related to this question, actually, this standard deviation of the K-normal distribution health scaling depends on the dimensionality of the previous layer, basically. So it's like 1 over the dimensionality of the previous layer. So you don't have like exploding effects on the output of the neurons, given that they're just random values.
Okay.
maybe following Peter's question, I have one extra question about how actually sparse is the final network. For instance, after you do the thresholding, is it very sparse, or it's kind of 50%, or it's more or less like a lottery ticket that you would kind of almost get rid of 99% of the parameters?
Francisco, would you like the answer?
Yeah, I mean, it depends, of course, on the model, on the task, but usually we get something like 20%. And the interesting thing is that usually if you look at the distribution of these, let's say, trainable probability mask, so these Bernoulli parameters, you have some like U-shaped distribution where you have a lot of probabilities close to 1 and many probabilities close to 0, basically, and just a few probabilities are like uncertain around 0.5. If the task is harder, like in very a small fraction of clients participate each round and a highly heterogeneous data set distribution, then you have more basically probability coefficient close to 0.5, meaning that the convergence is not like a good convergence of the model. Basically, it's uncertain about the value to assign to each weight, because in very simple and like full participation tasks, they know quite confidently that which parameter should be like close to 1 and which one should be close to 0, basically. So which connection you should take or remove from the network. So this is also an indication that indeed the model is not quite sure about the right final, let's say, structure of the network. So I guess maybe your also idea of having like this dropout Monte Carlo approach at the end to evaluate the model is also helpful to see, because in the very simple kind of task, you can see that the results are quite similar if you take many samples, but if you take many samples in this very harder kind of task and systems, then yeah, maybe you have a very kind of wide distribution on the results of the output.
Thank you for the insights. Yeah, because what I wanted to ask about, like, if the network is very sparse, whether you kind of observe this same phenomena as you had for like a lottery ticket, that you kind of like, you can't train that network from the beginning, only if it is like the lottery ticket. That was kind of why I was asking about that. But it seems like you said like it's kind of roughly 20%, right? So that shouldn't be that much of a problem. Yeah. Correct. Yeah, maybe we can wait for some other questions from the audience, if any. Yes, there is a question by Mohammed. Now, by the way, everybody can unmute themselves. I enabled that, so you don't need to raise any more your hand. Just unmute yourself and feel free to ask the question.
Okay, thank you. Could you kindly go to the table where you try to measure the bit per parameter? Where you mentioned, yeah. So could you please elaborate more on why you think I think this is an average, right? Run over many simulations. Why would it be that in your approach, it happens that you get less than 1 bit per parameter, while the others, for example, FedMask, for example, I read FedMask, so they get 1, for example. I'm not sure what's the reason. I mean, if you can just rate.
Yeah, sure. So in FedMask, so they don't have this like Bernoulli sampling operation. So in FedMask, they train some. So it's a different framework, but I can summarize it quickly. So they don't try to find any probability mask or anything. They just find these deterministic scores and then they threshold them. So what they communicate to the server is just like thresholded scores, and they threshold it in a way that like the binary values are like symmetric. And then when we do arithmetic coding or when we compute the entropy, it's just 1. So it's not smaller than 1 because everything is like uniform. But in our case, we don't have that symmetry in the binary mask that we communicate. So for example, like since we actually have this like sparsity larger than 50%, most of them, like majority of them are actually 0, and like a smaller than 50% are 1. So we actually, by doing arithmetic coding or like maybe another entropy coding, we can reduce the bit rate down to like 0.8, 0.9 sometimes. Is that helpful?
Yeah, so basically what you're saying that in FedMask approach, the frequency of ones and zeros are almost the same.
Yeah,
and
exactly.
your approach, given that you have this.
So it's the same story for sine SGD. So for example, sine SGD also like just communicates like 1 bit per parameter. And when we compute the entropy, we can't like gain anything because it's just the entropy is 1 because there is a symmetry between positive and like number of positive and negative parameters.
I see. Okay, thank you.